Do you know, when it comes to matrices and determinants, the area from where every examiner loves to ask questions is properties. Properties of inverse of a matrix, properties of adjoint of a matrix. So let's tackle this highly insightful past year JEE advanced question to check how strong is your grip over the properties. So here we have M to be a square matrix of order 3 with A and B as two real unknown entries. But adjoint of M is exactly provided to us. And the question is, which out of the given 4 options is or are correct? Take a close look at the options because we will be spending time with each one of them. First things first, because we are given adjoint of M in the question, we will quickly recall that adjoint of M is nothing but transpose of the cofactor matrix of M. And we have M with us. So let's go ahead and calculate the cofactor matrix of M. For that, we will have to replace every entry of M with its respective cofactor. Correct? Let's start with the 1/1th element, that is 0. What will be its cofactor? Well, for that, I will strike off the first row, strike off the first column. That will leave me with a 2 cross 2 square matrix. Its determinant will be 2 minus 3b. I will multiply this with minus 1 to the power 1 plus 1, thereby implying that 2 minus 3b is the cofactor of the 1/1th element. So I will replace 0 with 2 minus 3b. Moving on to 1/2th element, which is 1. What will be its cofactor? Well, strike off the first row, strike off the second column. That leaves you with the submatrix 1, 3, 3, 1. Its determinant will be product of diagonals minus product of off diagonals. That means 1 minus 9. That is minus 8. You multiply it with minus 1 to the power 1 plus 2. That leaves you with 8. So 8 is the cofactor of the 1/2th element. Replace 1 with 8. Similarly, you compute the cofactor for every other element, every other entry of M, and that will give you this to be the cofactor matrix of M. Once you reach till here, you have to take the transpose of this matrix. That means you simply have to interchange the rows and columns. When you do that, you end up getting the adjoint of M. But wait, we are already given adjoint of M in the question. And M can have a unique adjoint. That means both these adjoint matrices will be equal. And two matrices are equal if and only if their orders are same and their corresponding entries are same. Correct? So when you compare the corresponding entries, you will end up getting 2 minus 3b is equal to minus 1, which will imply that b is equal to 1. And along with that, ab minus 1 is equal to 1, which will imply that a is equal to 2. Bingo! The values of a and b are now known to us. So a plus b we can quickly calculate. It will come out to be 3. That means option D is absolutely correct. And from now on, whatever discussion that we are going to have now will be with the matrix M, with A replaced with 2 and B replaced with 1. So let's talk about option A now. The claim is determinant of adjoint of M square is 81. Wait a second. What is determinant of M first of all? Let's calculate. That's simple. I will expand with respect to the first row and my answer will come out to be minus 2. Alright, so determinant of M is equal to minus 2, which is clearly non-zero. This means M is non-singular and I can say M inverse exists. I need determinant of adjoint of M square. Wait, let me first talk about determinant of adjoint of M. Right? What is that? What is that? It is equal to determinant of M to the power n minus 1, where n is the order of M. Here, the order of M is 3. So my answer will be determinant of M to the power 3 minus 1, that is 2. So determinant of M is minus 2. So minus 2 squared gives me 4. That means determinant of adjoint of M is coming out to be 4. Now I need determinant of adjoint of M square. Correct? What will this be equal to? Determinant of M square to the power n minus 1. Now if m has order 3, m square will also have order 3. So you will have 3 minus 1 as the power, thereby implying determinant of m square to the power 2. But you know determinant of a to the power n is determinant of a whole to the power n for any n natural number. So what do you get in the next step? This is determinant of m to the power 2 times 2, that is 4. Now determinant of m we already know it is minus 2. So minus 2 to the power 4 will give you 16. Alright, that means determinant of adjoint of m square is coming out to be 16 and not 81. So option A is incorrect. Easy. Moving on to option B. It says m multiplied with the column matrix alpha, beta, gamma is equal to the column matrix 1, 2, 3. Then alpha minus beta plus gamma is 3. Basically, what is written in option C is a system of 3 linear equations in 3 unknowns alpha, beta, gamma. You can generate those 3 equations by simplifying this matrix equation. Okay? How exactly? Just substitute m as the original matrix which is given to us and expand the left hand side, equate it with the corresponding entries of the right hand side, and bingo, you have these 3 linear equations to be forming the system. And you can clearly see it's a non-homogeneous system. So you can use the Cramer's rule to compute the values of alpha, beta and gamma. They will come out to be 1, minus 1 and 1. The claim was that alpha minus beta plus gamma is equal to 3, which is exactly true because 1 minus 1 plus 1 is actually giving you 3. So option B is also correct. And now we are left to check just the last option, which is C. It says adjoint of m whole inverse plus adjoint of m inverse is equal to minus m. In order to check whether the claim made by this option is correct or not, I want you to recall a very, very important property which says that A times adjoint of A is same as adjoint of A times A, which is further equal to determinant of A times identity matrix of order n. Now what I want you to do is divide throughout the equation by determinant of A, keeping in mind that determinant of A is non-zero, or rather A is invertible. What do I get in the next step? A upon determinant of A times adjoint of A is equal to adjoint of A times A upon determinant of A, which is equal to identity matrix. Now interpret the language of this question. It says P into Q is equal to Q into P is equal to identity. Product of two matrices in any order is equal to identity. That means both of them are inverses of each other. So if A is a non-singular matrix, then inverse of adjoint of A is nothing but A upon determinant of A. This is a very, very important part that I want to share with you. This is exactly what we will be applying in option C. Here, determinant of m came out to be minus 2, which is non-zero, which implied m is invertible. And determinant of adjoint of m came out to be what? Determinant of m to the power n minus 1. That means minus 2 whole square, which is 4, which is also non-zero. So you are sure that determinant of adjoint of m is non-zero, hence adjoint of m is yes invertible. And what will be its inverse? M upon determinant of m. Agreed? Yes. So that means adjoint of m whole inverse will be m upon determinant of m. Okay? And what about adjoint of m inverse? Well, adjoint of m inverse is nothing but adjoint of m whole inverse, which is again m upon determinant of m. So what is this? 2 times m upon determinant of m. But determinant of m is nothing but minus 2. 2 cancels out and you are left with minus m. So the claim made by option C is absolutely correct. Adjoint of m whole inverse plus adjoint of m inverse is yes equal to minus m. So B, C, D are the three options which are correct and A is incorrect.